Good evening, everyone. Welcome to week 6 tutorial of the Applied Thermodynamics course. I am Thananka Sutia, PhD at IISc Bangalore, and we'll wait for some time. And in the meanwhile, let me share my screen. Okay, I think the screen is visible. Okay. Okay, so let us start today's class with the first question. It's given that calculate the ideal air standard cycle efficiency based on Otto cycle for a gas engine with a cylinder bore of 50 millimeter and a stroke of 75 millimeter and a clearance volume of 21.3 centimeter cube. Okay. Fine. Given bore is equals to 50 mm and that will be equal to 5 centimeter. Length is equals to 75 mm. This will be equal to 7.5 centimeter, and clearance volume VC is given to us as 21.3 centimeter cube. Okay, so from here we have to calculate the eta of an Otto cycle. Okay, so for that what we require is the formula for calculating the efficiency of an Otto cycle. Okay, so how will we calculate the efficiency of an Otto cycle? So first of all, let us look how an Otto cycle looks. So Otto cycle, it has 4 processes. Okay. uh, 2 constant volume heat addition oblique rejection processes, and 2 reversible adiabatic isentropic. Reversible adiabatic is directly isentropic, so I should not write it again. So 2 reversible adiabatic compression or expansion processes. Okay, so if we want to draw the PV diagram, okay, so the compression stroke 1 to 2, then there will be a constant volume heat addition. Okay. Okay, fine. So this will be work of compression WC, this will be work of expansion WE, and here constant volume heat addition will take place Q1, and here constant volume heat reduction will go out Q2. Okay, so 1 to 2 reversible adiabatic compression. Okay, 2 to 3 constant volume heat addition. Okay, 3 to 4 reversible adiabatic expansion, and 4 to 1 it's constant volume heat rejection. Okay, so if you want to look at the TS diagram, sorry, so the TS diagram will basically look like this. So 1 to 2 fine, 2 to 3, 3 to 4, and then 4 to 1. Okay. So now if we want to calculate the efficiency eta, this will be nothing but W net upon Q1. What is W net? Q1 minus Q2 by Q1. So that will be equal to 1 minus Q2 by Q1. Now how we can write Q2? 1 minus Q2 is nothing but CV times T3 minus T2. Okay, and Q1, I'm sorry, this is T4. Q2 is CV times T4 minus T1, and this is CV times T3 minus T2. Okay, CV cancel. So what we can write as eta auto is equals to 1 minus T4 minus T1 and T3 minus T2. So if we know the temperature at all the state points, then we can directly calculate efficiency from this formula of this particular cycle. Okay, but remember, in our question we are given only the diameter of the bore, the length of the stroke, and the clearance volume. Okay, so that means this formula we have to modify it. Now how will we do that? Okay, so for the process for the process 1 to 2, what we can write? T2 divided by T1 is equals to V1 divided by V2 to the power gamma minus 1. Yes or no? This is for a reversible adiabatic process. This thing holds good because PV to the power gamma is equals to constant in case of a reversible adiabatic process. Okay, so from here I can write T2 is equals to T1 into Rk to the power gamma minus 1, where Rk is equals to compression ratio is equals to volume before compression divided by volume after compression. Okay, and volume before compression is nothing but V1, and volume after compression is nothing but V2. Okay, so T2 in this equation I can write it as T1 into Rk to the power gamma minus 1. Okay, fine. Now similarly, what I can write as, since V1 is equals to V4 and V2 is equals to V3. Okay, because this 1 to 2 4 to 1 processes are constant volume process, and 2 to 3 processes are also constant volume process. Okay, so V1 is equals to V4 and V2 is equals to V3. Okay, so therefore what I can write again, T3 divided by T4 is equal to V4 divided by V3 to the power gamma minus 1. This I can also write as V1 divided by V2 to to the power gamma minus 1. This means what? T 4 is nothing but T3 by Rk to the power gamma minus 1. Is it clear? Clear? Okay, so this is, if I write this as 3 and if I write this as 2 and this equation as 1, so now equation 1 implies eta auto, that will be equal to what? 1 minus T4 minus T1 divided by T3 minus T2. Okay, so this will be 1 minus, what is T4? T4 is nothing but T3 divided by Rk to the power gamma minus 1, okay, minus T1, and this will be T3 minus T1 into Rk to the power gamma minus 1, okay. Fine, so this will be 1 minus, above if I will take the LCM, so this will be Rk to the power gamma minus 1, this will be T3 minus T1 into Rk to the power gamma minus 1, and this will also be T3 minus T1 into Rk to the power gamma minus 1. Okay, so these two will cancel out each other, so finally what I will get, eta auto is equals to 1 minus 1 by Rk to the power gamma minus 1. Okay, so if we know the compression ratio, then we can calculate the efficiency of an Otto cycle. Okay, so now from the given thing, can we calculate the compression ratio? That is our main task. Okay, so we are given D is equal to 5 centimeter, and we are given L is equals to 7.5 centimeter 7.5 centimeter, and we are given clearance volume Vc is equal to 21.3 centimeter cube. Okay, so therefore Vd, that is the displacement volume, will be equal to what? Pi by 4 times d square into L. Okay, so this will be pi by 4 times 5 square into 7.5 centimeter cube. Okay, so this one you will get as 147.26 centimeter cube. Okay, now therefore Rk is what? Volume before compression divided by volume after compression. Okay, so volume before compression is what? Vd plus Vc, and volume after compression is Vc. Okay, so from here we can get 1 plus Vd by Vc. Okay, so that means my Rk will be what? 1 plus Vd is 147.26 and Vc is 21.3. Okay, 47.26, 21.3. So you will get your compression ratio as 7.91. Okay, so this is your compression ratio. Now therefore eta auto will be equal to what? 1 minus 1 by Rk to the power gamma minus 1. Now what is gamma? What is they are taking that standard that they are taking the working fluid as air. So for air gamma is equals to 1.4. Okay, so from here I can get this one as 1 minus 1 by 7.91 to the power 0.4. Okay. So you'll get your answer as 56.27%. Okay, so we were given all the terms in case of volume. So if we would know the state points of the temperature, temperature at its state point, then this would have been the formula which we would be using for calculating the efficiency of an Otto cycle. But here we are given to find out the compression ratio first and then to calculate, so that's why this way we had to proceed. Okay, fine. So then let us move to the next question. An engine operating on Otto cycle has a compression ratio 8:1. At the beginning of the compression stroke, the air is at 103.5 kilopascal and 300 Kelvin. Now if the heat supplied is 920 kilojoule per kg, calculate the maximum pressure, the maximum temperature, and the cycle efficiency. Okay, so once again let us draw the PV and the TS diagram. Okay, okay, so this is 1 to 2, this is 2 to 3, this is 3 to 4, and this is 4 to 1. Okay, so here this is V equals to C and this is V equals to C. Okay, now here Q1 amount of heat is added and here Q2 amount of heat is rejected, and WE amount of work is done by the system and WC amount of work is done on the system. Okay, fine. And if you want to draw the corresponding PV diagram, so PV diagram if you want to draw, so this will be 1 to 2 compression, 2 to 3 constant volume heat addition, 3 to 4, and then 4 to 1. Correct. So here from here what is maximum pressure? Maximum pressure will be equal to your P3, and maximum temperature will be equal to your T3. So TS diagram will give us a hint of the maximum temperature, and PV diagram will give us which is the maximum pressure in this cycle. Okay, so what are the given things now? Given RK that is the compression ratio is equals to 8. Okay, at the beginning of the compression stroke, that means before the compression stroke, just before the compression stroke, that means at the point 1, P1 is given to you as 103.5 kilopascal. Okay, and T1 is given to us as 300 Kelvin. Okay, then heat supplied, that means heat added, so your Q1 is given to you as 920 kilojoule per kg. So therefore we have to calculate the maximum pressure and the maximum temperature and also the cycle efficiency from this, and CV is given as 0.718 and gamma is given as 1.4. Since Cp by Cv is equals to gamma, so from here Cp will be equals to gamma times Cv. Okay, so that is 1.4 into 0.718. You'll roughly get this one as 1.005 kilojoule per kg Kelvin. Okay, kilojoule per kg Kelvin. Okay, and if you treat this as an ideal gas, so R will be equals to what? Cp minus Cv, and that you will get this one as 0.287 kilojoule per kg Kelvin. Okay, so these are the parameters that we will be requiring in this one. So how to calculate the maximum pressure and maximum temperature? Okay, so we will calculate the temperature at each step, and then we will finally get the answer. So how to do? Yes, so we know that T2 by T1 is equals to V1 by V2 to the power gamma minus 1. This means what? T2 by T1 is equals to Rk to the power gamma minus 1. So from here T2 will be equal to what? T1 into Rk to the power gamma minus 1. So that means T2 is equals to, what is T1? 300. What is Rk? 8, and gamma minus 1 is 0.4. Okay, so from here you will get T2 is equals to 689.22 Kelvin. Okay, so this is your T2. Now what is how to calculate T3? Given again Q1 is equals to what? 920 kilojoule per kg. Okay, and also Q1 is equal to what? Cv times T3 minus T2. Clear? So from here 920 is equals to 0.718 times T3 minus 689.22. Okay, so from here T3 minus 689.22 will be equal to what? 920 by 0.718. So this will be 1281.34. So from here T3 is equal to 1281.34 plus 689.22, 1970.56 Kelvin. Okay, so this is your T3. Now then, how will we calculate T4? Simple. We know T3 divided by T4 is equal to what? V4 divided by V3 to the power gamma minus 1. Okay, similar to the first question. So again T3 divided by T4 will be equal to what? V1 divided by V2 to the power gamma minus 1. Why? Since V1 is equals to V4 and V3 is equals to V2. Okay, so that means what? T4 is nothing but T3 divided by Rk to the power gamma minus 1. Okay, so from here what is T3? 1970.56, and Rk is what? 8 to the power 0.4. Okay, 1970.56 divided by 8 to the power 0.4. So you will get this one as 857.74 Kelvin. So we have got temperature at all the steps. Okay, now what we need to just calculate? We need to calculate the pressure at the point 3. Okay, that means we need to calculate pressure at point P3. Okay, because we have got maximum temperature. So what is maximum temperature? Therefore my maximum temperature is equal to what? T3, and that is equal to what? 1970.56 Kelvin. Clear? Now how to calculate the pressure? Okay, so from this equation only we can also calculate P1 V1 to the power gamma is equals to P2 V2 to the power gamma. Yes or no? So that means what? P2 by P1 is equal to V1 by V2 to the power gamma. Okay, so that means what? P2 is nothing but P1 into Rk to the power gamma. Okay, so what is P2 then? P2 is equal to what is P1? P1 is 103.5 into what is Rk? 8 to the power 1.4. Okay, 103.5 into 8 to the power 1.4. So that is equal to 1902.24 kilopascal. Now for the process 2 to 3, what we can write? P2 V2 by T2 is equal to P3 V3 by T3. Now remember, V2 and V3 are equal, so this will cut down. So from here we will get P3 is equal to P2 into T3 divided by T2. Okay, what is P2? 1902.24. What is T3? T3 is 1970.56. And what is T2? T2 is 689.22. Okay, kilopascal. So from here P3 is equal to what? 1902.24 into 1970.56 divided by 689.22. Okay, so you will get this one as 5438.72 kilopascal. Okay, so therefore this is also equal to your maximum pressure. We have got the maximum pressure, we have got the maximum temperature. Now our task will be to calculate the efficiency of the cycle. Okay, so how will we calculate again? Eta auto, we have two formulas, one minus T4 minus T1 divided by T3 minus T2. Correct? Now we have already derived this in the previous question. 1 minus T4 minus T1 divided by T3 minus T2. Okay, so what is T4? 1 minus T4 minus T1. What is T4? 857.74. And what is T1? 300. Okay, what is T3? 1970.56. And what is T2? 689.22. Okay, you put all these values. 857.74 minus 300, 1970.56 minus 689.22. So you'll get this one as 56.47%. Okay, other way, that means the alternate formula also we can do. Eta auto, if you know the compression ratio, what was the formula? 1 minus 1 by Rk to the power gamma minus 1. So what is my Rk? Rk is 8. Okay, so 8 to the power 0.4. And this one also you will get this one as 56.47%. So by both the ways you will get the similar answer. Okay, fine. So let us go to the next question then. So this is a question of a diesel engine. An ideal diesel engine has a compression ratio of 20 and uses air as the working fluid. The standard, the state of the air at the beginning of the compression process is 95 kilopascal and 20 degrees Celsius. Now if the maximum temperature of the cycle is not to exceed 2200 Kelvin, determine the thermal efficiency of the cycle. Okay, so once again we have to derive the thermal efficiency of the cycle, but this time our cycle given is a diesel cycle. Okay, so diesel cycle, what are the different processes? So two reversible adiabatic compression or expansion processes are there, and then one constant pressure heat addition. Okay, remember in the Otto cycle the heat addition process was constant volume, but here the heat addition process is constant pressure and one constant volume heat rejection. Okay, so this is the, so all the processes are same, only the constant that the heat addition process is different. In the Otto cycle or the petrol cycle, the heat addition process was constant volume, but here our heat addition process is constant pressure. Okay, so let us first draw the PV diagram. Okay, so if this is my compression process 1 to 2, okay, now my addition process is, heat addition process is constant pressure. Okay, my heat addition process is constant pressure, so this is my 2 to 3. This is how the cycle will look at. Okay, the next is TS diagram. Okay, so this is my 1 to 2 and this is my 2 to 3. Now this will be P equal to C. Okay, then this is my 3 to 4. Now one interesting thing is that the slope of V equal to C and the slope of P equal to C curve, that will be different in a TS diagram. Okay, so if my P equal to C, so whether my V equal to C will be at a higher slope than this one or at a lower slope than this one, let us first check it. Okay, so what we can write, Q is equals to T ds is equal to C dt, correct? No, so that means what I can write, dt by ds is equals to T by C. Okay, now remember dt by ds is nothing but slope of TS diagram. Okay, dt by ds is the slope of TS diagram, correct? Now this dt by ds is inversely proportional to C. Now since Cp is greater than Cv, therefore dt by ds for P equals to constant must be less than dt by ds for V equals to constant. Okay, Cp is greater than Cv, it's inversely proportional, so the slope of the constant pressure process is less than the slope of constant volume process. Okay, so this actually it will look like, this will be at a much higher slope. Okay, so if I want to draw it properly, this slope will be lesser and this slope will be higher. Okay, so in diagrams this won't make it so difference, but I'm just giving you so that you should keep in mind that these two slopes are different. Okay, these two slopes are really different. Okay, so now what are the given things to us then? What is given to us? RK, compression ratio, is given to us as 20, and the state of the air at the beginning of the compression stroke, that means P1 is 95 kilopascal and T1 is 20 degrees Celsius, which I can write in Kelvin, that is 293 Kelvin. Maximum temperature, from these two diagrams we know that the maximum temperature is nothing but T3 and that is equal to 2200 Kelvin. Okay, and Cp and Cv values are given, which we already know. Okay, and from here gamma we can calculate this one as 1.4. okay. Correct. So now what we have to do, we have to calculate the efficiency of this cycle. Okay, so how will we do now? We will just calculate the temperatures at each step. Okay, so for the process 1 to 2, T2 by T1 is equals to V1 by V2 to the power gamma minus 1. Okay, so from here T2 will be what? T1 into Rk to the power gamma minus 1. And what is your T1? 293, Rk is 20 compression ratio, and gamma is 1.4, so this will be 0.4. okay, 293 into 20 to the power 0.4, so this is 971.13 Kelvin. Okay, so this is your T2. We have got T1, we have got T2, we have got T3. Now we just need to calculate T4. So how will we calculate T4? Any idea? Because in the earlier case your V4 was equals to V1 and V3 was equal to V2, but here this is not the case. Okay, so how will we go? P1 V1 is equals to RT1. So from here V1 will be equal to what? RT1 by P1. What is R? 0.287, T1 293, and what is P1? 95. Okay. So from here 0.287 into 293 divided by 95, so this is 0.885 meter cube. Okay, so this is your V1. Now V1 by V2 is equals to 20, so from here V2 is equals to V1 divided by 20, that is 0.885 divided by 20, zero point 044 meter cube. Okay, so you got V1, you got V2. Now how to calculate V3? For the process 2 to 3, okay, P2 V2 by T2 is equals to P3 V3 by T3. Now remember, this process 2 to 3 is a constant pressure process, because now our heat addition is taking place in a constant pressure process. So P2 is equals to P3. So from here V3 is nothing but V2 times T3 divided by T2. Now you got V2, that is 0.044. What is your T3? 2200. And what is your T2? 971.13. Okay, so from here V3 is equals to what? 971.13. 0.0996 meter cube. Okay, and V4 is equals to V1, and that is equal to your 0.855 meter cube. Why? Because this 4 and 1 is a constant volume process, isn't it? So 4 to 1 is a constant volume process, so therefore your V4 is equals to V1. So now from here it is very easy. For the process 3 to 4, what we can write as T3 divided by T4 will be equal to V4 divided by V3 to the power gamma minus 1. So from here T4 is nothing but T3 divided by V4 divided by V3 to the power gamma minus 1. Okay, so what is T3? 2200. What is V4? 0.855. And what is V3? 0.0996. And gamma minus 1 is 0.4. okay, 5 by 0.0996 to the power 0.4. okay, so from here you are getting T4 as 930.979 Kelvin. okay, so therefore eta diesel will be equal to what? 1 minus again Q2 by Q1. okay, but now 1 minus Q2 is the heat rejection process and that is a constant volume process, so this is CV times T4 minus T1, and heat addition process is a constant pressure process, so this is T3 minus T2. okay, so how it becomes actually 1 minus T4 minus T1 in divided by gamma into T3 minus T2. okay, so therefore eta diesel is equal to what? 1 minus T4 is what? 930.979. T1 is what? 293. Gamma is 1.4. T3 is 2200 and T2 is 971.13. okay, so from here you will get your efficiency 930.979 minus 293 divided by 1.4 into 2200 minus 971.13. okay, so you will get 62.92%. okay, so just like that Otto cycle, we also have an alternate formula. okay, so how to calculate that alternate formula? Alternate, this is when we know the temperature at each point. okay, so alternate formula for diesel cycle efficiency. okay, so till now we know that the eta diesel is equals to what? 1 minus T4 minus T1 by gamma into T3 minus T2. okay, now our idea will be to replace all temperatures in terms of T1. okay, so now T2 by T1 is equal to RK to the power gamma minus 1. so from here T2 is equals to T1 into RK to the power gamma minus 1. okay, fine. Any doubt? okay, so then what we know, P2 V2 by T2 is equals to P3 V3 by T3. now P2 and P3 are same constant pressure process, so from here T3 is equals to T2 into V3 by V2. okay, so now this V3 by V2 we name this as RC, where RC is equals to cutoff ratio. okay, cutoff ratio. Now again T3 is equals to T2 we can write in terms of T1. So T1 into Rk to the power gamma minus 1 into Rc. So this is your T3 in terms of T1. Okay, so one temperature is only left, T4. Again, what we can write, T3 divided by T4 is equals to what? V4 divided by V3 to the power gamma minus 1. Okay, now this I can write as T3 divided by T4. What is V4? Is nothing but V1 by V3 to the power gamma minus 1. Okay, now T3 divided by T4, this V1 divided by V3 I can write this one as V1 by V2 into V2 by V3 to the power gamma minus 1. Is it clear? I can write this way. Okay, so then what I can write, T3 divided by T4 is nothing but V1 by V2 to the power gamma minus 1 into 1 divided by V3 by V2 to the power gamma minus 1. Okay, so that means what? T3 divided by T4 is nothing but Rk to the power gamma minus 1 divided by Rc to the power gamma minus 1. Okay, now this one, then T4 is what? Is T3 divided by Rk to the power gamma minus 1 into Rc to the power gamma minus 1. Now what is T3? T3 is actually equal to T1 into Rk to the power gamma minus 1 into Rc. Okay, and into Rc to the power gamma minus 1 divided by Rk to the power gamma minus 1. Cancel out. So this one you will get this one as T1 into Rc to the power gamma. Okay, so T4 and this one. Now therefore eta diesel now 1 minus, once again I will write T4 minus T1 gamma into T3 minus T2. Okay, so eta diesel will be equal to 1 minus T4 is what? T1 into Rc to the power gamma minus T1 gamma. What is T1? T3 is T1 into Rk to the power gamma minus 1 into Rc minus what is T2? T2 is T1 into Rk to the power gamma minus 1. Okay, so from here eta diesel is equals to 1 minus T1 we take out, it will be Rc to the power gamma minus 1 divided by gamma into Rk to the power gamma minus 1 into T1, and that will be Rc minus 1. Okay, so this T1 and this T1 will cut out. So from here we'll get eta diesel is equals to 1 minus Rc to the power gamma minus 1 divided by Rk to the power gamma minus 1 into gamma into Rc minus 1. Okay, so this is another formula. If you just know the compression ratio formula for thermal efficiency of a diesel cycle based on compression ratio and cutoff ratio. Okay, so if you know only the compression ratio and the cutoff ratio, then this is basically the working formula. And if you put the same, means because you already have the values for the volumes of at all the points, so if you put the values you will again get the same answer. Okay, fine. So let us go to the next question then. Now this question is for dual cycle. So an air standard dual cycle with compression ratio 18 has heat addition process as two equal halves, so that 1000 kilojoule of heat is added at constant volume, followed by 1000 kilojoule of heat added at constant pressure. Now at the beginning of the compression process, the pressure is 100 kilopascal and the temperature is 25 degrees Celsius. Now determine the temperature at each point on the cycle thermal efficiency in the network. What would be the thermal efficiency if 75% of the total heat addition took place at constant volume? Okay, so first ABC part will be belonging to whatever things is given, and then the heat input, that is total heat input, we have to modify it such that 75% is added at a constant volume. So how a dual cycle looks like? Dual cycle. Okay, the only difference is that heat addition takes place both in constant pressure and constant volume. Okay, so that means what? The only difference again, once again, will be lying in here is the heat addition process, where now the heat addition process will be split into two processes. In one part, or in one half or whatever quarter or whatever time of the way, it will be in a constant volume process, and the second half will be in the constant pressure process. Okay, fine. So which one happens first? That one only we should just look into here. Okay, so if we draw the PV diagram, okay, so this is the compression stroke which will have no any change. Okay, then what happens? This is one, this is another, and then it comes here. Okay, so this is 1 to 2. If I mention this 2 to 3, and this is 3 to 4, and this is 4 to 5, and then this is 5 to 1. Okay, so heat addition process is 2 to 4, which is split into number A 2 to 3 constant volume, and number B 3 to 4 it's constant pressure. Okay, so this is the case. Now if we draw the TS diagram, so how will we look? This is our 1 to 2 compression stroke. Okay, now I already told you that constant volume slope will be higher, so we'll write like this: a higher slope, this is 2 to 3, and then less higher slope, this is 3 to 4. Okay, then 4 to 1, and then less higher slope. Okay, fine. Actually this should not come down. Okay, now what are the things that are given to us then? RK, compression ratio, is given to us as 18. Okay, heat addition is split into two halves, so Q 2 to 3 is equal to 1000 kilojoule per kg, and Q 3 to 4 is also given as 1000 kilojoule per kg. Okay, at the beginning of the compression stroke, that means the point 1, P1 is given as 100 kilopascal. Okay, and T1 is given as 25 degrees Celsius. Okay, that is 298 Kelvin. Now we have to just determine the temperature at each step. That means we know T1, we have to find T2, we have to find T3, we have to find T4, we have to find T5. Okay, this is the overall idea of this question. Then we have to calculate the thermal efficiency of the cycle, then we have to calculate the network, and then modifying the input and all these things, we will get the last part, that is the part D. Okay, so temperature at each point. Temperature at each point. So how will we calculate? Now T2 by T1 is what? V1 by V2 to the power gamma minus 1. Till now you know these things, we have no any doubt, I think. So this will be T1 into Rk to the power gamma minus 1. Again this is an air, so gamma we already know. So what is T1? T1 is 298, compression ratio is 18, and gamma minus 1 is 0.4. okay, 298 into 18 to the power 0.4, that will be 946.95 Kelvin. This is your T2. Okay, now Q223 is equals to 1000. Okay, this implies what is Q223? Constant volume process, so CV times T3 minus T2 is equals to 1000. Okay, what is CV? CV is 0.718, T3 we don't know, minus T2 is 946.95 is equals to 1000. So from here T3 minus 946.95 is equals to 0.718, that is 1392.76. okay, so from here T3 is equal to 1392.76 plus 946.95, that is 2339.71 Kelvin. okay, similarly Q324 is also equal to 1000. Now Q324 will be Cp times T4 minus T3 is equal to 1000. okay, what is Cp? 1.005 kilojoule per kg Kelvin. T4 we don't know, and T3 is just now we calculate 2339.71, and that is equals to your 1000. okay, so from here T4 minus 2339.71 will be equal to what? 1.005. This will be 995.025. so from here T4 is 995.025 plus 2339.71, and you will get this one as 3334.735 Kelvin. okay, so we have got T1, we have got T2, we have got T3, we have got T4. Now our task will be to calculate T5. okay, now for that, at the 0.5 we should know one more parameter, then only we can do. So what are the parameter we know at the 0.5? At the 0.5 we know that the volume is equals to V5 is equals to V1. okay, so now same thing we will be doing just like we are doing in the diesel cycle. okay, so now P1 V1 is equals to RT1. so from here V1 is equals to 0.287 into 298 divided by what is your P100. okay, 0.287 into 298 divided by 100, you'll get this one as 0.855 meter cube. Now V1 by V2 is equals to what? Compression ratio is given as 18. so from here V2 is equals to 0.855 divided by 18. okay, 0.855 by 18, this will give you your 0.0475 meter cube. This is V2. okay, now 223 is a constant volume process, so this is also equal to your V3. yes or no? 223 is a constant volume process. Now next P3 V3 by T3 is equals to P4 V4 by T4. now 0.324 is a constant pressure process, so from here V4 is equals to what? V3 into T4 upon T3. okay, so what is V3? 0.0475. what is T4? T4 is 3334.735. and what is your T3? T3 is 2339.71. okay, so from here V4 is equals to 0.0475 into 3334.735 by 2339.71. okay, so V4 will be equal to 0.068 meter cube. Now what we can write, T4 divided by T5 is equal to what? V5 divided by V4 to the power gamma minus 1. Now what is V5? V5 is equals to V1, because the process 5 to 1 is a constant volume process, and V1 we have just now calculated as 0.855 meter cube. okay, so from here T5 is equals to what? T4 divided by V1 divided by V4 to the power gamma minus 1. What is T4? 3334.735. What is V1? 0.855, and V4 is 0.068 to the power gamma minus 1 is 0.4. okay, so if you put all this 3334.735 by 0.855 divided by 0.068 to the power 0.4, so you will get this one as 11211.37 Kelvin. So we have got temperature at all the steps. okay, now what is the second part? The cycle efficiency, that is the cycle thermal efficiency. okay, thermal efficiency of the cycle. okay, so this one once again eta will be equal to what? W net by Q1. As usual we know what is W net is nothing but Q sorry, actually in this process we are not using this Q1, basically this will be Q input. okay, and what is W net? That will be Q input minus Q output divided by Q input. okay, so 1 minus Q output by Q input. okay, so Q input is already given to us, yes or no? 1000 and 1000, so that is equals to 1 minus 2000. And what is Q input? Sorry, Q output is nothing but CV times T5 minus T1, yes or no? Because this 5 to 1 is the only process where your heat rejection is taking place. It's 5 to 1. okay, so that's why this is the formula. Now 1 minus what is CV? 0.718. okay, what is your T5? T5 is 1211.37. okay, and what is T1? It is 298 divided by 2000. okay, so eta will be now equal to 1 minus 0.718 into 1211.37 minus 298 divided by 2000. okay, so you'll get this as 67.2%. okay, fine. So next is what would be next we have to also calculate net work. okay, so what is net work? W net will also be equal to what? Q output, actually it's Q input minus Q output, I'm sorry, Q input minus Q output. okay, so what is your Q input? 2000 and what is your Q output? CV times T5 minus T1. Okay, 2000 minus 0.718 into 1211.37 minus 298. Okay, 0.718 into 1211.37 minus 298, and this is 2000 minus, so this one is 1344.2 kilojoule per kg. Okay, so that is your W net, that is the net work done. Okay, now next is what it is telling, thermal efficiency if the total heat addition 75% of the total heat addition takes place in the constant volume process. So when 75% of total heat addition takes place in constant volume. Okay, so that means what? Therefore Q 223, okay, that is the constant volume process, is 75 by 100 into 2000, because the net heat addition was 2000. Okay, that is kilojoule per kg. Okay, so 0.75 into 2000, you will get this one as 1500 kilojoule per kg. Okay, so therefore Q 3 to 4 will be what? 2000 minus 1500, and that will be equal to 500 kilojoule per kg. Okay, so now just variation will be in the efficiency, how the variation will take place, because now the intermediate temperatures will change. Yes or no? So how will we calculate again then? So we will already be having T1 as 298 Kelvin, and there will be no effect in T2 because the process 1 to 2 is not affected. Okay, so what is the T2 that is calculated in the earlier will be the same. So T2 will be nothing but 946.95 Kelvin. 946.95 Kelvin. Okay, so the effect will be seen in T3. Now Q223 is equals to 1500. That means what? CV times T3 minus T2 is equals to 1500. Okay, so that means 1500 divided by 0.718 is equal to what? T3 minus 946.95. so from here T3 will be what? 1500 by 0.718 plus 946.95. okay, so T3 is 3036.086 Kelvin. 086 Kelvin. Okay, so this is your T3. Similarly, your T4 will also get changed. Q3 to 4 is now just 500. Okay, so that means Cp times T4 minus T3 is equal to 500. So from here I will get 500 divided by 1.005 is equals to what? T4 minus what is T3? 3036.086. okay, so from here T4 is what? 500 divided by 1.005 plus 3036.086. okay, so this is 3533.59 Kelvin. okay, so T1, T2, T3, T4 is gone. Now again to calculate T5 we will require the volume, and for that your V1 will again be the same. There will be no any change. 0.855 meter cube, and this will also be equal to V5, and your V2 will be equal to the other V2 because the process 1 to 2 is not affected. So V2 is 0.0475. 0.0475 meter cube, and this also will be equal to V3. Okay, now P3 V3 by T3 is equals to P4 V4 by T4. Now this is a constant pressure process, so this goes down, so therefore V4 will be nothing but V3 into T4 upon T3. So what is V3? 0.0475. now this T4 and T3 are changed. T4 is 3533.59 and this is 3036.086. okay, so from here V4 is equals to 0.0475 into 3533.59 divided by 3036.086. okay, so this will be your 0.055 meter cube. So now from here we can calculate your T5, yes or no? Now T4 divided by T5 is equal to V5 divided by V4 to the power gamma minus 1. So from here T5 is nothing but T4 divided by V5 is equal to V1, so V1 by V4 to the power gamma minus 1. So what is T4? 3533.59 and what is V1? 0.855 and what is V4? 0.055 and gamma minus 1 is 0.4. okay, so from here T5 is equal to 3533.59 by 0.855 divided by 0.055 to the power 0.4. okay, so T5 is 1179.16 Kelvin. okay, so therefore eta now will be equal to 1 minus Q output divided by Q input. Once again your Q input is 2000 because we have just changed the input values in different processes, not the total heat input. okay, so this is due to now Q out will be again CV times T5 minus T1. okay, so this will be 1 minus what is CV? 0.718, T5 is 1179.16 and this is 298 divided by 2000. okay, 1179.16 minus 298 divided by 2000. okay, so you will get this one as 68.36%. so when you have changed the heat addition in constant volume, then the efficiency is also changed. okay, fine. So let us go to the next question then. A 4-cylinder 2.5 liter SI engine operates on a 4-stroke air standard Otto cycle at 3000 rpm. The engine has a compression ratio of 8.6, mechanical efficiency of 86%, stroke to bore ratio of 1.025, fuel is isooctane with air fuel ratio as 15 and a heating value of 44,300 kilojoule per kg and a combustion efficiency of 100%. At the start of the compression stroke, the conditions of the cylinder are 100 kilopascal and 60 degrees Celsius, and it is assumed that there is an exhaust gas of 4% residual left over from the previous cycle. okay, so then you have to calculate the pressure and temperature, indicated thermal efficiency, indicated mean effective pressure, brake power, torque, brake mean effective pressure. CP is given as 1.108 and CV is given as 0.821 and gamma is given as 1.35. okay, fine. So what are the things that are given? Given number of cylinders is equal to 4. okay, the total displacement volume is equals to what? 2.5 liter. okay, then it is a 4-stroke SI engine So that means your Otto cycle will work. It's a 4-stroke SI engine. Okay, then your RPM N is given as 3000 RPM, revolutions per minute. Your compression ratio RK is given as 8.6. okay, eta mechanical efficiency is given as 86%, that is 0.86. okay, then stroke to bore ratio L by D is given to you as 1.025. okay, and air fuel ratio is given to you as 15. okay, calorific value of the fuel is given to you as 44,300 kilojoule per kg. okay, and eta combustion is given to you as 100%, that is 1.00. okay, now at the start of at the start of combustion, P is given as 100 kilopascal, and next T is given as 60 degrees Celsius, and also 4% exhaust is left from the previous cycle. okay, so these things are basically given to us. So now let us try to solve this question then. Displacement just a minute. Displacement volume of each cylinder is equal to what? 2.5 divided by 4 liter, and that is equal to 0.625 liter. okay, if you express this in meter cube, this will be 0.000625 meter cube. okay, so this is the displacement volume of each cylinder. Now we know that compression ratio RK is what? VD plus VC upon VC. That means 1 plus VD upon VC. So from here, clearance volume VC is nothing but RK divided by, clearance volume will be equal to VD divided by RK minus 1. okay, so what is VD? Displacement volume is 0.000625. what is RK? Compression ratio is 8.6 minus 1. okay, you'll get this one as 8.22 into 10 raised to the power minus 5 meter cube. okay, that is VC is equals to what? 0.0822 liter, or you can also write this one as 82.2 centimeter cube. okay, so this is your clearance volume. Now therefore VD, we can also write this one as pi by 4 into d square into L. yes or no? Again, since L is equals to 1.025 d, so from here what we can write? Into d square into 1.025 d. okay, so that means pi by 4 into 1.025 d cube is equals to VD, which is equals to VD, which is equals to if this was in VD, that is equals to 0.000625. okay, so from here D will be equal to what? 4 into 0.000625 divided by pi into 1.025 to the power 1 by 3 in meter. okay. 4 into 0.000625 divided by pi into 1.025 to the power 1 by 3. So you will get this one as 0.0919 meter or 9.19 centimeter. Okay, so therefore length of the stroke will be equal to what? 1.025 into d, which is given in the question. So that is equal to 1.025 into 9.19 centimeter. Okay, 0.025 into 9.19. So this will be approximately equal to 9.42 centimeter. Okay. Now at stage 1, okay, T1 is equal to 60 degrees Celsius, and this is equal to 333 Kelvin. Okay, and P1 is equals to 100 kilopascal. Okay, and therefore V1 is equals to what? Vd plus Vc. Okay, so this is 0.000625 plus 0.00000822, and which will be equal to 0.000707 meter cube. Okay, therefore mass of gas mixture in the cylinder will be equal to mm is equals to P1 V1 by R of T1. Okay, so what is P1? 100. What is V1? 0.000707. Okay, what is R? 0.287. and what is T1? T1 is 333. Okay, this one you will get this one as 0.000740 kg. Okay, so this is the total mass, whether it can be air, it can be fuel, it can be residual mixture, whatever it is. Okay, stage 2 is compression. So stage 1 was combustion, now stage 2 is compression. Okay, so P2 is equals to P1 into Rk to the power gamma. Till now we know this thing. So what is P1? P1 is 100, Rk is 8.6, and what is gamma? Gamma is 1.35. Okay, 100 into 8.6 to the power 1.35. So this one you will get at 1826 kilopascal. Okay, similarly T2 will be equal to T1 into Rk to the power gamma minus 1. What is T1? 333 into 8.6 to the power gamma minus 1 is 0.35. Okay, you'll get this one as 707 Kelvin. Okay, now similarly V2 will be equal to mRT2. This is basically mass of the mRT2 upon P2. What is m? 0.000740, R 0.287. What is T2? T2 is 707, and your P2 is 1826. Okay, you put all these values, you'll get this one as 0.000822 meter cube, and which we already got this one as approximately, this is the same as the Vc. Okay, which we should also get. So therefore this is the clearance volume of one cylinder. Okay, now what actually happens that this mass of gas mixture mm, which we have got in the previous equation, in the cylinder, okay, is made up of air. Okay, if we consider the mass of the air as ma, and it is also made up of fuel, okay, which is say mass mf, and exhaust mixture. Okay, that it's telling that 4% exhaust is already left, so let me assume this as ma. So this mm composed of ma and this composed of ma, mf and m exhaust. So now our task will be to separate out the mass of the air, the mass of the fuel and the mass of the exhaust mixture. Therefore, mass of air, what will be the mass of air? We know the air fuel ratio is 15, so out of 16, if 16 is the total kg of the mass of the air and the fuel, then 15 by 16 will be basically the mass of the air. So 15 by 16, correct? Fine. Into 0.96. Why 0.96? Because 4% of them are exhaust. Okay, so because whatever mass of the air and the fuel total combined, mass of the mixture, out of them 4% is exhaust. So remaining, if you subtract the exhaust from the whatever you have got, then only you will get basically your mass of the air and the fuel. So therefore it's 0.96 times whatever mm you have got, 0.000746 kg. Okay, if you do this, you will get this one as 0.000666 kg. So this is the mass of the air that is present in the mixture. Okay, similarly mass of the fuel also we can calculate. Mass of the fuel will be what? 1 by 16 times similarly 0.96 times 0.000746 kg. Okay, so this one, if you will get calculate, you will get this one as 0.00044 kg. Okay, now again mass of the exhaust, it's very simple, because it is telling us that the 4% is mass of the exhaust. So that means 4 by 100, that is 0.04 times whatever mass of the mixture was there, 0.00746 kg. Okay, so this will be 0.000030 kg. Okay, fine. Now stage 3. What is the third stage? We have completed the combustion process, we have completed the compression process. Now heat will be added. Okay, so heat addition. Okay, Q1, that heat addition, what we can write, mass of the fuel into calorific value of the fuel into eta combustion. Yes or no? Because there should be some combustion efficiency. Even if you put fuel, the total mass of the fuel may not be get converted into this one. So but here our efficiency is 100% is given to us. So that Q1 will be equal to mass of the fuel we have already calculated, that is 0.000044. Okay, calorific value of the fuel is given to us as 44,300 kilojoule per kg, and the combustion efficiency is given to us as 100%. So that's 1.00 will be the multiplication factor of this one. Okay, so this is one way by which we can calculate the heat input. Okay, now this Q1 also, this Q1 will be equal to what? For the combustion process, the Q1 will be equal to the mass of the mixture. Okay, and since this is an SI engine, so heat addition takes place in the constant volume, so this will be CV times T3 minus T2. And what is T2? We have already got this one as 707 Kelvin. So from here we can calculate the temperature T3. Okay, so put the value of Q1 here, 0.000044, sorry, 044 into 44300 into 1 is equals to, what is mass of this one is 0.000746. Okay, CV is remember this is not air, so they have given the CV value as 0.821. Okay, so 0.821 into T3 minus 707. Okay, now if you put all these values here, you will get T3 is equal to 3915 Kelvin. Okay, this is the temperature at the point 3. Similarly, our task is to not only calculate temperature, we have to calculate the volume, we have to calculate the pressure also. But since this is a constant volume process from 2 to 3, therefore V3 is equal to V2, which we have already got. Okay, and that is equal to your Vc, that is your clearance volume, 0.0000822 meter cube. Okay, now our task will be to calculate pressure. So P2 V2 by T2 will be equal to P3 V3 by T3. Again, we know that V2 is equals to V3. So from here, P3 is equal to P2 into T3 divided by T2. We have all the values of P2, T3 and T2. If you put this, you will get this one as just put it P2. What is P2? 1826. What is T3? 3915. And what is T2? 707. So this will be in kilopascal. Okay, so your P3 will be 1826 into 3915 by 707. Okay, so this will be 10111 kilopascal. So almost 10,000 kilopascal. So very high pressure it's dealing, and also this is a multi-cylinder, so it will be dealing. Okay, now stage 4. That will be your power stroke, that is your expansion stroke. Okay, so now for the expansion stroke, that is at the point 4, we have to calculate the temperature, the pressure and whatever thing. Now T3 divided by T4 will be equal to what? V4 divided by V3 to the power gamma minus 1. Okay, now since this is an IC engine, so V4 since this is an SI engine, so V4 is equals to V1 and V3 is equals to V2. Okay, if you remember that this if you draw this PV diagram, okay, like this it will look. So if this is 1, this is 2, okay, this is 3 and this 4, so this one and this one volume same, and this one and this one volume same. This is just what I have done. So this I can write this one as T4 is equals to T3 divided by V1 by V2 to the power gamma minus 1. And what is V1 by V2? It's nothing but the compression ratio RK. Okay, so that is RK to the power gamma minus 1. Now we have already got the value of T3 is 3915 and RK is 8.6 and gamma is 1.35, so this will be 0.35. Okay, you put these values, you will get T4 as approximately equal to 1844 Kelvin. Okay, similarly P4 will be equal to P3 divided by RK to the power gamma. Okay, so this you will get as 554 kilopascal, and V4 we will get as mm times R T4 upon P4. Okay, put these values, you will get this one as 0.000707 meter cube. Just in justification of that V1 is equals to V4, because we will always get the same values. Okay, now therefore the work of, that is the power stroke, that's the work of expansion, what we will get this W3 to 4. So remember the adiabatic formula, this is P3 V3 minus P4 V4 upon gamma minus 1. Okay, so this is the formula for adiabatic expansion if it's going from adiabatic work done going from process 3 to 4. Now another way of writing this one, if it is an ideal gas, we can write this one as mm R times T3 minus T4 divided by gamma minus 1. Okay, fine. Now if we put all these values, you'll get this one as 1.257 kilojoule. Okay, similarly, what will be the work of compression then? W1 to 2, that will be P1 V1 minus P2 V2 upon gamma minus 1. So that will be what? Again mm times r into T1 minus T2 times gamma minus 1. We have all these values. If you put this, of course you will get this one in negative because this is a work of compression. So this will be 0.227 kilojoule. Okay. So therefore, what is the net work then? Net work will be W324 plus W122, which you will get as 1.030 kilojoule. Okay. So this is your net work. Heat added, we have not done the calculation for this one. We have just put in order to calculate the temperature at the point 3, but now we will just find out what is the heat addition value, what was the mass of the fuel we are using. MF 0.000044, 0.000044, calorific value is 44,300, and combustion efficiency is 100%. So if you put this, you will get this one as 1.949 kilojoule. Okay, so therefore indicated thermal efficiency is equals to what? W net divided by Q1. What is W net? Just now we have got 1.030, and what is Q1? 1.949. Okay, if you put this, you will get this one as 52.9%. Okay, therefore indicated mean effective pressure. Okay, so indicated mean effective pressure will be what? W net divided by V1 minus V2. Okay, 1649 kilopascal. Therefore indicated power will be what? W net into RPM we have already got, okay, divided by small n. Now this small n is equal to 2 here because it is a 4-stroke cycle. Okay, so 2 cycles per revolution you are doing. Okay, so that's why this will be 1.030 into RPM given as 3000 divided by 60. We are expressing in revolutions per second, and this is equals to 2. So from here you will get this one as 103 kilopascal. So we have got indicated power. Okay, so again we need to calculate what? Mean piston speed. Mean piston speed. So we already know the mean piston speed formula is 2 into L into N. Okay, 2 into S into N or 2 into L into N, whatever. This means that twice times the product of stroke into RPM. Okay, so put all these values. 2 into L. What is L? L is 9.42 centimeter. So we'll express this in meter. 9.42 divided by 100. Okay, so this is meter, and 3000 divided by 60. Okay, so you'll get this in meter per second. Then put all these values, you will get this one as 9.42 meters per second. Okay, now we are given eta mechanical efficiency. Okay, what is the mechanical efficiency they are giving? 86. Okay, 86% mechanical efficiency, 0.86, 0.86. Now we know that eta mechanical is equal to what? Brake power divided by indicated power. So from here, brake power is equals to what? Eta mechanical into indicated power. So brake power is equal to 0.86 times 103 kilowatt. Okay, this will be equal to 88.6 kilowatt. Again we know that brake power is equals to torque into 2 pi into n. So therefore torque will be equal to what? Brake power divided by 2 pi into n. Okay, so you put these values, you will get this answer as 282 Newton into meter. I am quickly writing this because we have all these values. You just have to convert it into SI unit. You will get these values. Now again we need to find out the friction power lost. So friction power loss is what? Is equal to indicated power minus brake power. Yes or no? So this will be equal to what? Indicated power is given as 103 kilowatt, and brake power we got as 88.6 kilowatt. So just the difference of this, you will get this one as 14.4 kilowatt. Okay, friction power loss. Now last part we have to calculate is brake mean effective pressure. Okay, now just like brake power, the brake mean effective power will be equal to what? Mechanical efficiency into indicated mean effective pressure. Okay, what is mechanical efficiency? 0.86, and indicated mean effective pressure we have already calculated as 1649 kilopascal. 1649 kilopascal. So from here you will get this one as 1418 kilopascal. Okay, so this is what the question was. Okay, now let us go to the next question then. Okay, so it's telling us that a small 5-cylinder CI automobile engine operates with a variable valve timing control system without a camshaft at operational speed of 3500 revolutions per minute. The intake valve opens at 32 degree before TDC and closes 57 degree after TDC. Okay, after BDC, and the exhaust valve opens 52 degree before BDC and valve opens at closes at 21 degree after TDC. Now again the similar things are given at idling speed. So for both the speed, one for the control speed, that is the operational speed, and other for the idle speed, we have the angles at which the inlet valve opens and close and the exhaust valve opens and close. We have to calculate the valve overlap in crank angles and valve overlap in time. Okay, in both the case, means one for operational speed and one for idle speed. Okay, we have to calculate valve angles, that means crank angles, valve overlap in crank angles, and valve overlap in time. Okay, so case 1, just we will draw the figure, you will get the idea. Case 1, that is operational speed. What will be the scenario at the operational speed? Okay, suppose if this is my TDC, okay, and if this is my BDC, okay, sorry, just this should be in straight line. Okay, now suppose this is the center. What it is telling us, that our exhaust, first of all let me go to the inlet valve. The inlet valve opens 32 degree before BDC. Okay, it opens 32 degree before BDC. Okay, and it closes 57 32 degree before TDC, 32 degree before TDC. Okay, so inlet valve opens 32 degree before TDC. So this is your inlet valve opens, and your inlet valve closes 57 degree after BDC. So this is the BDC. So after BDC, this one. Okay, this is your 57 degree, and this is your inlet valve closes. Similarly, your exhaust valve opens 52 degree before BDC. Okay, this is your 52 degree, and this is when your exhaust valve opens. Okay, and what it is telling us, that the exhaust valve closes 21 degree after TDC. So exhaust valve closes 21 degree after TDC. Okay, now then overlap angle is what? Overlap angle at TDC, this will be equal to 32 plus 21, that is equal to 53 degree. Okay, so 53 degree per 360 degree revolution. Okay, overlap angle at BDC will be what? BDC will be 57 plus 52, and that is equal to 109 degree per 360 degree rotation. Okay, now this is your overlap angle in crank angles. Okay, and one more case in real time. Sorry, yes, overlap angle in real time now. Okay, so this was your overlap angle in crank angle. Okay, for crank angle, just in terms of angle. Okay, so that means per 360 degree revolution of the crank, 53 degrees the overlap angle at TDC and 109 degrees the overlap angle at BDC. Now at TDC, rotation R1 is equals to 53 degree per 360 degree revolutions. Okay, and our n operational speed is given to us as 3500 rpm. Okay, that means this much revolutions per minute. So therefore, simple, you can calculate the time as rotation angle per n, because in one revolution there is 360 degrees. So basically it's telling us that 53 degree per revolution. Okay, this is 53 degree per revolution. Okay, so you have to calculate the time. So you have revolutions per minute, so you just divide it, you will get in this one in terms of time. Okay, so if you put this R1 is 53. Okay, and you can express this in pi radian or whatever if you want to do. I am just writing in degree, and this is in rpm. So finally now if you convert this in radians and whatever do, you will get this one as 4.206 into 10 to the power 5 minutes. Okay, and this will be expressed in terms of millisecond, 2.52 milliseconds. Okay, similarly at BDC, your R2 is what? 109 degree we have got. So just T2 you have to calculate this one as R2 divided by N. Okay, so you will get this one again, 5.1904 milliseconds. Okay, next is our case 2, that is your idling speed. Okay, now operational speed was there, and that operational speed that was given to us as 3500 rpm. Now our idling speed is given to us as what is your idling speed is given as 400 rpm. Okay, so now for this case we have to do the same thing. Okay, now suppose if this is my TDC and if this is my BDC. Okay, fine. So here it is telling us that the inlet valves opens 12 degree before TDC. Okay, so this will be now 12 degree before TDC. This is your inlet valve opens. Okay, and the inlet valve closes 18 degree after BDC. Okay, 18 degree after BDC. So this is your 18 degree, and this is what your inlet valve closes. Similarly, your exhaust valve opens 21 degree before BDC. Okay, so this is your 21 degree. This is your exhaust valve opens, and exhaust valve closes 8 degree after TDC. So this is 8 degree, that is exhaust valve closes. Okay, so therefore overlap in terms of crank angle now. Okay, so overlap at TDC is nothing but 12 degree plus 8 degree, and that is 20 degree, and overlap at BDC is equals to 18 degree plus 21 degree, and that will be equal to your 39 degree. Now similarly, overlap in terms of real time. Okay, so at BDC, start with TDC, whatever. At TDC, R1 is equal to 20 degree, so therefore T1 is equal to R1 divided by N. Put all these values, you'll get this one in 8.33 milliseconds. Okay, similarly at BDC, your R2 is equal to 39 degree, so therefore T2 is equals to R2 by N, and that you will get as 16.5 millisecond. So very simple question. So just a question that is related to valve timing diagram. Okay, fine. So now let us go to some questions of combustion. Okay, calculating the air fuel ratio and so and so forth. Now 2 kilomole of octane is burnt with air that contains 40 kilomole is burnt with air that contains 40 kilomole of air. Okay, now assuming the products contain only carbon dioxide, water, oxygen and nitrogen, determine the mole number of each gas in the product and the air fuel ratio of this combustion process. Okay, so how will we do this one? Air is contains of both oxygen and nitrogen. Okay, so what is the formula for octane? Octane is C8H18. Okay, so it's telling us 2 moles of octane and it reacts with 40 kilomoles of air. So air will be O2 plus 3.76 N2. Okay, now it is telling us that it contains carbon dioxide, it contains water, it contains oxygen and it contains nitrogen. Okay, so let me write this one. We don't know how many moles of oxygen carbon dioxide is there. I am writing this as X, this is Y, this is Z, and say this is W. Okay, now how this came, I think you are all aware of this one, that air contains 79% nitrogen and 21% oxygen by volume. Okay, so from here it came because we know that volumetric that means the volume fraction is approximately equal to the mole fraction. Okay, so volume fraction is approximately equal to mole fraction, so if you do these things you will get this as 3.76. okay, so now what our idea will be to find the value of X, Y, Z and W. Okay, so for that we will just balance. Now balancing carbon in the left hand and the right hand side, what we will get, 2 into 8, this is in the left hand side, and that is equal to X, so that means X is equals to 16. Okay, balancing the hydrogen part, so hydrogen part in the left hand side will be 2 into 18, there is no any hydrogen in the left hand side left. Now in the right hand side, that is 2 into Y. Okay, so from here Y is equals to 18. Similarly O, balancing for oxygen, this side will get 40 into 2. Okay, and this side will get 2 into X, okay, plus Y plus 2 into Z. Okay, so that means what, 80 is equal to 2 into X, X is 16, so 2 into X is 32. We already got the value of Y, plus 2Z. Okay, so from here Z is equal to 15. Clear? Now Let us balance for nitrogen then. Balancing for nitrogen will be 40 into 3.76, okay, into 2, and that will be equal to 2 into W, okay. So that means W is equals to 150.40, okay. So therefore the complete combustion equation is what? 2C8H18 plus 40 O2 3.76 N2, okay. This gives 16 CO2, that's the value of X. Value of Y was 18 H2O, and value of Z was 15 O2, and plus 150.40 N2, okay. So this is the complete. Now determine the mole number of each gas in the product, okay. So therefore number of moles in the product is what? So carbon dioxide we have 16 number of moles, water we have 18 number of moles, oxygen we have 15 number of moles, kilomoles, sorry, and nitrogen we have 150.40 kilomole, okay, fine. Next is what? We have to calculate air fuel ratio for this combustion process. So therefore air fuel ratio based on mass. We can also calculate based on mole, which we will be doing in the next question, okay. So what is this? Simple, mass of air divided by mass of fuel. Now what is the mass of air? This is the air, so you just have to calculate the mass of this one, okay. So 40. What is the mass of oxygen? 32, okay, and 40 into 3.76, this is the number of moles of nitrogen, and what is the mass of this one? Is 28, okay. So this is the mass of the air. And what is the mass of the fuel? Fuel is what? It's octane, so it's 2 into 8 into 12. This is for the carbon part, and for the hydrogen part it is 2 into 18 into 1, okay. So this is your air fuel ratio will get as 24.08, okay, fine. So let us go to the next question then. Determine the air fuel ratio both on a molar basis and mass basis for the complete combustion of octane with number 1 theoretical air, and number 2 150% theoretical air, that is 50% excess air if you are using. So first of all what we will do, we will just calculate the theoretical air part, okay. Theoretical air, okay. So octane, so C8H18, okay. So that means for 1 kilomole, how much mole of air we require, we don't know, so I am assuming this as A, and similarly this came, okay. Now since this is a complete combustion, so there will be no extra product, there will be carbon dioxide, there will be hydrogen, and since nitrogen is an unreactive compound, so your nitrogen will be left. So I am naming this one as B, this one as C, and this one as D, okay. So our again will be to balance this one. So again balancing the carbon, what we get, 8 is equals to B, okay. Balancing the hydrogen, what we get, 18 is equals to 2C. So from here C is equals to 9, okay. Balancing the oxygen, what we get, 2A is equals to 2B plus C, okay. So to A is equals to 2b means 16 plus c is equals to 9. So from here a is equals to 12.5. okay, and balancing for nitrogen, what we get, a into 3.76 into 2 is equals to d into 2. okay, 2 got cancelled out, so that means d is equals to a into 3.76, a is equals to 12.5. you put this, you'll get this one as 47. So that means now, therefore, the complete combustion reaction is what, C8H18 plus 12.5 times O2 plus 3.76 N2. And this gives 8 CO2 plus 9 H2O plus 47 into N2. okay, therefore air fuel ratio based on molar basis, that will be equal to what, number of moles of air divided by number of moles of fuel. okay, so the number of moles of air is what, 12.5 into 1 plus 3.76. okay, and number of moles of fuel, we are taking this as 1. okay, so this you will get as 59.5. okay, this is your air fuel ratio. Next is air fuel ratio based on mass is equals to what, mass of air divided by mass of fuel. okay, so mass of air will be 12.5. okay, this is the number of moles. Now 32 plus 3.76 into 28, just like the previous question, and this will be 8 into 12 plus 18 into 1. okay, you put this, you'll get this one as 15.05. okay, now next is 150% theoretical air, or we can say this one as 50% excess air. okay, so now we already know the complete combustion equation if there is only if you require the theoretical air. So what is the complete combustion equation? C8H18 plus 12.5 times O2 plus 3.76 N2, and this will give you 8 CO2 plus 9 H2O plus 9 H2O plus what is this, 47 N2. okay, 47 N2, this much we will get. Now we have to use 50% excess air, so that means now instead of this it will be 1.5 times this one. okay, so what will be happen, will it change the amount of carbon dioxide and this product? No, it will always form the same. okay, that means what, that whatever excess amount of oxygen you are adding, okay, that comes out in terms of oxygen only, and we don't know how much it will come. But one thing, it will change again. Here also 1.5 will be getting multiplied in nitrogen. Why? Because it is, we are using 150% theoretical air, so nitrogen 50% excess is coming here, no? And this nitrogen is unreactive, so it will remain here. Clear? So therefore balancing for oxygen will get 2 into 1.5 into 12.5 that will be equal to 2 into x. 2 into x plus 16 plus 9. Okay, so from here x you will get as 6.25. so therefore the complete combustion reaction reaction the complete combustion reaction is what? C8H18 plus 18.75 O2 plus 3.76 N2 gives 8 CO2 plus 9 H2O plus 6.25 O2 plus 70.5 N2. Okay, so therefore air fuel ratio on molar basis is equals to what? 18.75 into 1 plus 3.76 divided by 1, that will be 89.25. and air fuel ratio on mass basis that will be equal to 18.75 into 32 plus 3.76 into 28, okay, divided by 8 into 12 plus 18 into 1. Okay, so this one you will get 22.57. Clear? So then let us go to the next question now. Actually the time is not there today to solve these two questions. We will solve these two questions in the next class, and then we will start with the next week's whatever we are teaching, that numerical questions. Okay, thank you very much.